The next section of Physics 111, that's section 6, is all about stationary points and how to classify them, which also means that we're going to define and use second-order derivatives and then apply second-order differentiation to parametric differentiation and also implicit differentiation. Let's start section 6. In order to define what a stationary point is and how we can get them by using derivatives, let's recall how we define a derivative from first principles. If you remember from section 4, that's playlist 4, if you don't, maybe have a look at it back so you understand how we obtain this formula to obtain derivatives from first principles. We obtained a quantity that we called dy dx when we were thinking about these being very, very small displacements. And we've seen that essentially this quantity would go to the actual derivative of f of x when we take dx to 0. Essentially the same definition that we have above. Another way to look at this is that this quantity dy dx is approximately equal to the derivative at a specific point, which means that if you look at the change of the function, this change will be approximately equal to the derivative at that point times this small displacement. It is not equal, it is approximately equal. It only becomes equal if we deal with limits. This means that if we want to find out points for which there is no variation in the function, we're essentially looking at points for which dy is 0. The way we've defined dy is the small difference between the value of the function at x and the value of the function at x plus this very small quantity dx. And this implies that if we think about a point, say x equals a, if for a specific point x equals a, the derivative of the function is equal to 0, then it implies that this change in the function at that specific point is 0. This implies that because dy is approximately equal to the derivative times dx, this is a non-zero quantity. If this is the case, then dy is approximately 0. And this is the reason why we can use derivatives to find stationary points. We're essentially looking at points at which the rate of change is 0, and therefore this quantity, the change, will also be 0. But let's define this in a more mathematically rigorous way of what the stationary point really is. Now, as you have in your lecture notes, that's section 6.1, we're going to define the stationary point thinking in terms of a general point, in this case x equals c, and we say that this point x equals c is a stationary point if for a given function f of x, the derivative at point x equals c is equal to 0. In other words, if you want to find stationary points, what you need to find are points at which the first derivative equals 0. And that typically involves, in this case, we have a function of just x. It's just solving one equation. When we have functions of more than one variable, it will be about solving systems of equations. Once you find a stationary point, and this is the formal, very simple definition, it's a point at which the first order derivative is 0, there's still three possibilities for what the stationary point might be. For example, it may be a local maximum. And we'll see exactly which conditions it needs to satisfy for you to know that it is a maximum, and specifically a local maximum. Number two, it can be a local minimum point, or it can also be an inflection point. The important question now is, how do we decide if we're in the presence of case number 1, 2, or 3, or in other words, whether the stationary point is a maximum, a minimum, or an inflection point? A very simple way to do this is actually to look at what the function is doing just left and just right of the stationary point. Let's try to use this. A simple way to look at this is to maybe get a table and have a look at all different possibilities. So let's say that we have a point x equals c that we know it's stationary. This means that the derivative of a function f of x at point x equals c is 0. The simplest thing you can do in order to classify the stationary point in terms of these three different cases is to look at the sign of the derivative, just left and just right of x equals c. So let's try to put all the different cases and see if we can classify them. What we're going to do is, first of all, we know that the derivative is 0. This will be true for any stationary point, regardless of its nature. But what we want to find out is essentially what the derivative is doing when x equals c, but from values which are just below c. So I'm going to use this minus as notation for it. We also want to know what the derivative is doing when x equals c from values just above it. So I'm going to use a plus. We can then sketch what we think f of x is doing. And finally, we can conclude. Let's assume that for a given function f of x at this point x equals c, that the derivative is positive, just left of the point, and then it is negative, just right of the point. If we try to sketch what this means for this point x equals c, it means that to the left of it, the function is going up, and then to the right of it, the function is going down, which means that we're in the presence of a local maximum. If we have the reverse, say we have minus just left of the stationary point and plus just right of it, it will look similar but completely inverted. It means that at this point, this is stationary point, x equals c, x equals c. The derivative is negative, which means the function is decreasing when it approaches, and then when you go to the right of it, it's increasing. I'm going to do it just to avoid x equals c. We're in the presence of a local minimum. The other two cases are when the sign of the derivative is positive, both left and right, and the final case is when it's negative, both left and right. What are these cases telling us about the stationary point? Again, thinking about x equals c, x equals c, which is a stationary point because the derivative is 0. In this case, it means the function is going up when you approach the point, and after it is still going up. Again, I'm just avoiding the point, so the shape of the curves are not really meant to tell you anything, but the way they're behaving is. This means that we have an inflection point, and in a similar way, but kind of reversed, in this case we're seeing that the function is going down, and then it keeps going down, which means we also have an inflection point. These are essentially the four different cases for a function f of x. If you find a stationary point, this is a neat, simple way that you can use to classify them, which is looking at the sign of the derivative, just left and just right. It is also quite helpful to try to sketch it before you can classify them so that you're absolutely sure. But one thing that we will be able to look at is, instead of looking at the sign of the first derivative, is we can move a level up, calculate the second order derivative, and actually use it to classify the stationary points.